Hi everyone, and thank you very much for having me here. We are going to talk about collaborative filtering. So just before I present you the outline of the talk, I'd like to take a few seconds to explain what collaborative filtering is so that we are all clear on what we are going to do. Okay, so I think everyone knows basically what a recommender system is. The most famous examples come from Amazon or Netflix, this kind of stuff. And they help users answer questions such as what book should I read, what movie should I look at, what restaurant should I try, etc. And we distinguish usually between three kinds of recommender systems depending on the kind of information that is leveraged to output the recommendation. The first kind is the content-based systems, where we will represent our item by a set of features that are based on the content of the items, based on the metadata. This is usually used for recommending text documents, but I'll take the example of a movie recommender system. If you're recommending movies, you can represent your items by the actors that playing, the film director, the movie genre, etc. And you will try to match a user profile to a given kind of movies. So if you have a science fiction fan, you will try to recommend science fiction movies to this guy. This works okay, but we usually prefer to use collaborative filtering techniques. And in collaborative filtering technique, we are able to leverage social information about the user or the item. And this usually takes the form of user item ratings. We know that this user has rated this item with this value, and we can make recommendation based on this. The most classical example is the neighborhood method that we are going to describe next. And this basically, if you need to recommend some items to a given user, you will try to find some guys that have the same taste as this user, and you will recommend some items that those guys, that we call the neighbors, have liked and that this user hasn't rated yet. And the last kind of system is the knowledge-based system. It's usually used for very complex items such as computers, car, mortgage, loans, etc. And these are items where the knowledge about the domain is much more important than anything else, hence the name knowledge-based. And it's quite difficult to give a precise definition of the system because they are very task-specific, so we will ignore them anyway and just focus on the collaborative filtering problem, okay? And in particular, we will focus on the rating prediction problem, which is this. We have a set of past ratings, okay, that we put in a matrix that is extremely sparse because not all the items have been rated by all of the users. And in this matrix, so about 99, it's even more of the entries are missing, and the rows represent users and the column represent items, okay? So we have, for example, here Alice, Bob, etc. And the items, I'll just take the example of movies, could be, for example, Titanic, Toy Story, etc., etc., okay? And our mission here is to predict the missing value, all right? So just a quick word about me. I'm a PhD student in Toulouse in the south. I'll be defending in 3 weeks, so I'm almost done, which is great. And basically, I needed a library. I needed to make a few experiments on recommender systems. And there was no library at the time that suited really my needs, so I decided to make it. And I'm going to present that also during this talk. So finally, the outline. I'm first going to present you the neighborhood approach that I quickly described. This is a very, very simple algorithm that helps answer this rating prediction problem, okay? This is an algorithm that will help us fill in the gaps in this matrix. Next, I will describe you or detail the surprise, which is the library that I made. There's a website, you can Google it if you want. If you want to take a look during the talk, don't hesitate to do that. Also, don't hesitate to interrupt me if there's something you don't understand. And in the last part, if we have time, I'd like to talk about a little bit matrix factorization, which is another kind of algorithm for the rating prediction problem, which I really like. I find it really interesting. It's a little bit more complicated than the first one, but it's more interesting, I think. So let's go for the first part, neighborhood methods. The problem is this. We have a history of past rating. This is the matrix that I showed you before, and we need to predict the rating of Alice for Titanic, okay? Once we know how to predict the rating of Alice for Titanic, we know how to to predict the rating for any user and for any item. So this is a two-step algorithm. It's very simple. You first find the users that are similar to Alice, those that like the same movies as Alice, and those that dislike the same movies as Alice. And then you average the rating for Titanic, and you get your prediction. This is based on the assumption that if Alice and those guys that we call the neighbors of Alice, if they usually agree on their ratings, they will also agree on a rating that Alice has not yet rated, okay? So that's as simple as that. For the first step, for finding the neighbors of Alice, we will need a similarity measure, okay? Now, there are tons of ways to compute a similarity between two users. The most simplest one would be, for example, to count the number of common items, okay? If Alice and Bob have rated a lot of items in common, then they probably like the same movies. The thing is that we are not taking into account the rating values here, okay? We can see that Alice and Bob have 3 ratings in common, and Alice and Zoe also have 3 ratings in common. So if we're using that, we will say that Alice is as close to Bob as she is close to Zoe, which is kind of false. If we take a look at the rating values, we can see that Alice and Bob are actually really close. 2 is close to 1, 2 is close to 3, 5 is equal to 5. So Alice and Bob are fairly similar. But Alice and Zoe are quite different on their rating. They usually disagree on the rating values. So there are various similarity metrics. They basically do all the same jobs. They have different mathematical properties. I'm not going to detail this because we don't care. Some of them work best than some others. Honestly, it's not really interesting here. But yeah, they all do the same things. And if you want to try, usually what you do is try some measure, see if it works. If it doesn't, you try another one, and that's all. So there are tons of measures. And really, the only thing you need to know is that they can assess how close two users are one to another. All right, so that's it for the first part. And the second part for averaging the ratings. So we have seen that Alice is close to Bob, and we need to predict the rating of Alice for Titanic, which is the first column. We said that Titanic was the first column. So we need to predict the red question mark here. And we've seen that Alice is closer to Bob than she is to Zoe, so probably Alice have rated Titanic with a rating of 1. We'll do something like that. And of course, here I only showed Bob. This is the only neighbor that we found here. But we should usually aggregate more than 1 rating, okay? So really, that's just it. So if I were to ask you to write a piece of code that predicts the rating for a given user and a given item, you'd probably end up with something like this. It really fits in 4 lines of code. First line, you retrieve all the guys that have rated your item I, or Titanic if you want. Second line, you sort them given their similarity to Alice. And the next 2 lines are just the average, the weighted average of the rating for Titanic, okay? It's really just as simple as that. This is the math formula that may look scary if not used to it, but honestly it's just 4 lines of code, okay? So, is that it? No. You can do about 5 million more things. I won't go into the detail of this, but the very classical thing to do is rather than compute similarity between users, you can compute similarity between items. You can do both in the same time. You can learn the similarities instead of using a heuristic such as cosine similarity or this stuff. You can do tons of things. I won't go into the detail, but I just gave you the basic idea, I think, or I hope. All right, so that's it for the neighborhood method. We're now going to talk about surprise, which is the library that I made that helps building such algorithms, such as the one we just described, and that helps analyzing them and comparing them. So it's rather a library for rating prediction algorithm, okay? So it's not really saying that it's a library for recommender system is maybe too too wide. It's just a library for rating prediction algorithms. So why I made that? So as I told you, I needed a library that for my PhD. And at the time, I tried a lot of libraries. None of them really suited my needs because first, I didn't know what they were computing. Most of them were were not really transparent on the ratings, on the algorithms. For example, they were saying, okay, this is a neighborhood approach with a cosine similarity, but I didn't know how they computed the cosine similarities. So when I needed to compare my algorithm to them, I didn't know what I was comparing to, which was extremely frustrating. And I needed to really hack into very quickly to build an algorithm and just try if it works or not. So I decided to make it started very hacky. Please don't look at the code at the beginning. You'll faint. But I tried to make it better later. So why not scikit-learn? Right, scikit-learn is one of the best libraries for doing machine learning, and recommendation is kind of a machine learning task. Or at least we treat it this way nowadays. And actually, scikit-learn was made for tasks such as regression, classification, or some other unsupervised learning. But the rating prediction problem is actually quite different from that of classification. In our regression, for example, in classification on the matrix on the right, we will try to predict a dependent variable, the last column here, a dependent variable that we call usually y, based on some other predictor variable that we usually call x. But we can't do that for a rating prediction problem. There is no such thing as a y variable. The dependent variable doesn't exist because we need to predict ratings everywhere in the matrix, in every column, in every row, okay? So if you do classification, yeah, you can use scikit-learn, there's no problem. You can define your classifier, fit some data to some dependent variable, and then predict some stuff. With a recommendation problem, you can't do that. You can try, it won't work very efficiently. I just need to take a... In the meantime, please Google surprise. Okay, so the basic workflow of surprise is like this. I try to make it as simple as possible. First, you load a dataset. We'll see how to do that later. You can use built-in dataset or custom datasets. From this dataset, you construct a train set, which is just like it's the same data, but it's organized in a much more handy way for surprise to manipulate. You define an algorithm, you train it on your trace set, and then you're ready to make some prediction. Okay, that's it. The train method is, I don't know why I didn't call it fit. The scikit-learn is fit. I should have named it fit, but I named it train. I don't know why. It's too late now anyway. So we'll see the main features of surprise one by one. The boring stuff comes first, then it will be a little bit more interesting later. But just, I try to make dataset handling very easy. So you can load built-in datasets such as the movie dance or the gesture dataset that are very classical dataset in recommender system research. It will be downloaded automatically if you haven't already have it on the hard drive. You can of course use a custom dataset for your own database, and you can load data from a pandas data frame as well. I forgot to mention the license is BSD, so you can do whatever hell you want with surprise. Now I've already implemented a fair bit of algorithm. Most of them are not most of them, but some of them are matrix factorization, SVD, SVD++ that we are going to view later, non-negative matrix factorization, KNN, etc. And various similarity metrics are already built in. And I didn't describe them earlier, so you don't know what this is probably. Just the few lines of code here are how to to configure the similarity matrix that you want. So for example, here we're using the cosine similarity. We are not computing similarity between users, but between items instead. And we're using a minimal support of 10, which means that if two items have only been rated by less by 10 users, we will discard the similarity and put it to 0. And that's it. Okay, as I told you, I needed to have a very quick way to build a recommender for prediction algorithms. So if you want to do your own prediction algorithm and try to do some stuff, you only have to do two things. First, you create a class and inherit from the class algobase, and then create an estimate method, which takes two parameters, the user, the item, that's all. And you return a rating that you want to predict. So here I'm returning 3, which is quite dumb, but it works, okay? So when I will train my algorithm on the data set. Here the train method does absolutely nothing. And if I want to predict the rating of Alice for Titanic, I call the predict method, which will then call the estimate method. It just does a little bit of checking, like if the estimate method returns a rating that is not in the rating scale, like if your rating scale is 1 to 5, and the estimate method returns 6, it will fit it to 5. It just calls basically the estimate method. So you can of course do some more complicated stuff, like you can override the train method. For example, here we want to return the mean in the estimate method, the mean of all the ratings. So we just compute it in the train method, like in the fit. This is the fit method of scikit-learn. We just compute it in the train method, and then return it in the estimate method. The train set object that is passed to the train method has a lot of tools to make it easy for you to build your recommender systems. Much of them are iterators over users, over items, and over ratings. So, and this is the neighborhood approach that I described earlier. Basically, in the train method, we will compute the similarities between all pairs of users. Okay, I didn't write that. And then the estimate method fits on a few lines of code. This is basically the same as before. I just changed a little bit of code here, and this will work. This will also give you a 0 division error, but don't worry, in the real code of surprise, I checked for that. Really, it's just as simple as that. Okay, now a little bit more complicated stuff. When we do some research on recommender systems, well, the ultimate goal of your system is to predict all the red check marks here. This is what you ultimately want to do. Unfortunately, when you have an algorithm, if you predict those red check marks, you have absolutely no idea if your predictions are correct or not, simply because you don't know these values. So what we do to assess the quality of our recommender system is usually cross-validation, just the exact same way we do with classification or regression, right? We will hide some of the non-ratings. So the checkbox here, some of the checkbox will become blue question marks. We will hide them, train on the known check marks, that we call it the train set, and test our algorithm on the blue question marks, okay? And we call this the test set. We will compute the RMSE, it's just the average error between our prediction and the real value, and we square the error so that bigger errors are very, very, very bad. Like if you have an error of 1, it will stay an error of 1. If you have an error of 2, it will become an error of 4. If you have an error of 3, it will become an error of 9, etc., etc. And we do that many times. So we will just hide some of the item first, compute the train, and compute the RMSE. Then we will hide some other ratings, and we'll do that again and again and again until we have predicted all of the ratings that we know. And this is the cross-validation process, okay? And you can do that very easily in Surprise by just loading a dataset, whether it's built-in or your own dataset, etc. Then split your dataset into different folds with the split method. Define your algorithm, and the split method will give you an iterator over the folds of your cross-validation procedure. So you can now do like this for the train set and the test set. In each of my fold, I train on the train set, then I get all the predictions, and then given the predictions, you can then compute the RMSE or other prediction accuracy metrics. So, okay. And you can also do some grid search. So there is also this feature of in scikit-learn. We have, in fact, entirely stolen here from scikit-learn. If you don't know what grid search is, basically if you have an algorithm that takes various parameters and you don't know which combination of parameters works best, you do some grid search. So you specify the values of the different parameters that you want to try, and the grid search will do all the nasty stuff for you. It will try every combination, find the metric that you want to evaluate, and give you the best estimator over this set of parameters, okay? So I told you about RMSE. There are other useful accuracy metrics. For now, the only built-in measures are RMSE, MIE, which is basically the same as RMSE, except that we don't square the errors, and FCP, which is a fraction of concord pairs, and this is a more rank-based metric. You can also compute top-end related measure very easily. I haven't built that in because it actually depends on the recommendation strategy that you use, but you can still do that very efficiently or very easily. And you can dump your algorithms if you want. So let's say you have run some grid search, you get your best algorithms, you don't want to lose it, just drop it on the hard drive and then come back later to use it. You can also dump the predictions. That's actually very useful. If you run an algorithm on a set of prediction and another algorithm on the same set of predictions, then you can use it with pandas to compare the two algorithms. And the fact that the two data frames will have the same indexes allows you to do some kind of nice query, such as, okay, give me the prediction when this algorithm has an error of, or I don't know, 5, and when this one performs better than this one, etc. So you can really have nice comparison of your algorithms this way. All right, what time is it? Okay, I have 10 minutes to explain you what matrix factorization is. What took me 2 years to understand. Let's go. So this is a bit scary. I'll try to avoid the pain as much as possible. No, really, this can be really math involved. I'll try to give you the intuitions behind these models because they are really, really cool, in my opinion. The math are also extremely important, but I'll try to avoid it as much as possible, okay? So, the Netflix Prize. The Netflix Prize was a contest run by Netflix about 10 years ago. And the idea was this: if you can improve our RMSE by 10%, we give you $1 million. Some people did it, some people became rich. During this Netflix Prize, one of the most efficient algorithms that came out was algorithms that were based on matrix factorization. So we're going to describe them. The one we're going to describe is based on SVD, which stands for singular value decomposition. It's a highlight of linear algebra. It's a beautiful result. And before we get to SVD, we need to go into PCA, which is almost as awesome as SVD. So forget the recommendation problem for a moment and consider this. We're going to see what PCA does. I give you 400 grayscale images, okay? 1 pixel is just a value between 0 and 1. And you take all of these faces and flatten them into a big matrix, okay? So the first row of your matrix is the first line, is the first image that you have flattened. The second row of your matrix is the second image that you have flattened, etc., okay? And you do that for all the faces. A PCI is an algorithm that will give you these creepy guys on the top, okay? It will give you 400 of these creepy guys. And the cool thing about these creepy guys is that they can build back all of the original faces. This one is the first faces that we have, and this is the reconstruction. It's actually a GIF. So yeah, here we see it's the beginning of the reconstruction. So at the beginning, the face is very blurry, and then it starts to converge toward the real face of the guy. And PCA gives you the creepy guys, and it also gives you how much of the first creepy guy this one needs, how much of the second creepy guy, how much of the third creepy guy, etc., until the last one, okay? It can reconstruct, with the creepy guy, you can reconstruct all of your initial faces. I love it, honestly. Okay? So let's go back to the rating prediction problem. You can do that on a rating matrix also, okay? You can do that on a rating matrix if your rating matrix is entirely dense. When there are no missing entry, and there are a missing entry in our problem, we'll just assume that there are no missing entry, okay? In our initial matrix, we had faces in the rows that were images. Now we just have users represented by the items, by their ratings. And PCA will reveal, instead of revealing creepy guys with their faces, they will reveal typical users. So I put back the reconstruction of all the faces. I love it. But in the recommendation setting, the users, the typical users, can also build back all of our initial users. So we had Alice in the first row of our matrix. Now Alice is just a sum about some typical users or some typical raters, okay? It may be, for example, 10% of the first one, which is, or 10% of the first one, 10% of the second one, 50% of the third one, etc., until the end. The same goes for Bob, but the coefficients for Bob are different. And the nice thing is that we can associate a semantic meaning behind each of the typical users. So for example, well, in practice there is no way to do that in a very accurate way, but it helps to understand. We can consider that the first guy is some typical action fan, the second guy is a typical comedy fan, etc. So Alice will be represented by a 10% action fan. She's not very sensitive to comedy, but she very much likes romance, etc., etc. And we can also do the same for items. If we just transpose our matrix, the columns which are moving now becomes the rows, okay? So instead of having users in the row, we have items in the row. And we can also do that for the movies. So Titanic will be 20% action, I just made that up, 70% romance, something like that, okay? These coefficients will be revealed by PCA. And now we can explain what SVD is. SVD is just performing PCA, but 2 times on the rows and on the columns at the same time. In one shot, it will give you the typical users and the typical items, okay? So this is what the matrix factorization looks like. It will give you the typical users in a matrix that we call U. It will give you the typical items in a matrix that we will call M. And just focus on this part here. This is the matrix multiplication, M times UT. This is our matrix factorization. Now it has a very nice way. That's just a thing I want you to understand here. It has a very nice way of modeling the ratings. So with this model, the rating of user U for item I is represented as a scalar product of two vectors. The first vectors that we'll call PU is just a vector representing the user U, okay? So PU in the case of our users is just a vector containing 10%, 10%, 50%, etc., etc., okay? And the vector QI here, PU times QI, the vector QI is the same but for the items. So QI for Titanic will be 20%, 0%, 70%, etc., etc. And the rating of user U for item I will just be a sum of concepts. These concepts being action movies, romance movies, comedy, etc. And it will capture the affinity of Alice for these concepts time the affinity of Titanic for these concepts. So for example, we've seen that Titanic is a 12% action movies. Alice, kind of like action movies, so okay. The rating will be 20% times 50%, plus 0 times 0, plus 70 times 80. So probably the rating of Alice for Titanic will be high in with these values. Instead, the rating of Bob is, okay, he kind of like action movies, but he really likes comedy, and comedy is not a feature of Titanic. This feature has been revealed by the data. And Titanic is a romance movie, but Bob doesn't really care about romance movies. So the movie of Bob for Titanic will probably be lower than that of Alice, okay? So I hope I could give you a good intuition of how this thing works. The big problem now is to compute the two matrices, the matrix M and the matrix U, blah, 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 stochastic gradient descent. And it fits in 1, 2, 3, 7 lines of code. That will work badly, but that will work. You actually need to do a little bit more stuff for it to work best, but honestly, it's not really more complicated than that. You just NBS the ratings, so you take into account the fact that some users tend to be nicer than some other. You take also into the fact that some items tend to be rated higher than some other, and you use regularization to avoid overfitting, and you get an algorithm which is called SVD, which is not SVD. There's a lot of confusion because of that. This is only a this is inspired by the SVD of linear algebra, okay? But this is still quite different because we are trying to fit a model where all the ratings are missing, so this is really, really not the SVD of linear algebra, even if it has a lot of features in common. So in the end, this kind of algorithm is just your good old-fashioned machine learning statistical paradigm, okay? You just assume a model for your data, you fit your observation for your data, and then you pray to God, and you hope for the best, because if your model is incorrect, then you will have very bad prediction. But it usually works very well. Okay, so just a few remarks. Surprise, as I told you, is mostly a tool for prediction algorithms, for algorithms that predict ratings. I often get asked, hey, can I use that in my prediction system? Honestly, I don't know. If you're predicting ratings, it will be helpful. If you're not predicting ratings, it will not be helpful. I would recommend you to take a look at MangaKey, which is made by Jiljen here, which is a good example of a real production-ready recommender systems. Surprise was aimed to be as easy to use as possible. I tried to make a really great documentation to avoid frustration. It's not aimed to be the most efficient implementation, okay? So I'm not saying it's slow, I'm just saying it's not the best implementation. So there are other libraries that do this job well. And last thing, yeah, I plan to, for now, mostly explicit ratings. Algorithms for explicit ratings are implemented. Explicit ratings are like 1, 2, 3, 4, 5, stuff like that. And implicit ratings are usually binary ratings that this user has clicked on this ad, etc. These are binary ratings, and the algorithms are quite different from for explicit ratings and for implicit ratings. So I'm trying to work on implicit ratings now. That's it. Thank you.